In this paper, we investigate the problem of action quality assessment, which aims to automatically score an Olympic game or surgical activity. Conventional approaches simply regard action quality assessment as a regression problem, which results in unsatisfactory performance. The root of such a limitation is that this kind of treatment disregards for the inherent uncertainty of the score labels in practice. As an example of a diving action, when the athlete finishes the action, 7 judges will give their scores. After deleting the top 2 and bottom 2 scores, the final assessment is calculated based on the difficulty degree and the scores from 3 judges. Due to the different judges and their subjective appraisals, there is inherent uncertainty in the final score label. Besides the diving game, this phenomenon exists in many other sports like gymnastic vaults and figure ski. To address this, we propose an uncertainty-aware score distribution learning method for action quality assessment. During the training phase, we first generate a Gaussian distribution based on the score label. Then the input video is divided into several segments and fed into an i3D backbone to extract features. After passing through 3 fully connected layers, the obtained features are fused by temporal pooling and pass through a softmax layer to output the predicted distribution. We optimize the Kullback labeler divergence loss between these 2 distributions. During the testing phase, we forward the input video into the trained model, and the final assessment is obtained by selecting the score with the max probability. When fine-grained score labels are available, we further devise a multipath model to exploit the disentangled components. During the training phase, we model the scores from different judges as different Gaussian distributions. We utilize a similar strategy as before to build a model containing multiple subnetworks. Then we optimize a multitask learning loss function to train our model. During the testing phase, we obtain the final assessment based on the predicted score and the rule of the game. In order to verify the effectiveness of our approaches, we conduct experiments on 2 sports datasets and a surgical activity dataset. Here are some results in the 3 datasets, which demonstrate the advantage of our methods compared with the state-of-the-art. In this figure, we show a visualized result of the score distribution change in temporal domain. The x, y, z axis represents the clip number, the score, and the probability of different scores. The 7th and 8th clips are highlighted because the athlete falls to the ground, which leads to salient low score predictions. We further show 2 cases in the MTL-AQA dataset. The first is a successful case where the final scores predicted by our methods will match with the ground truth. The second is a failure case where the ground truth of the video is 0 as the athlete falls into the water directly. This time, our methods give the score far higher than the ground truth. This result indicates that when assessing videos with extreme scores, the proposed method may not be able to get satisfactory results due to the scarce samples. In conclusion, to address the uncertainty in the score label for action quality assessment, we propose an uncertainty-aware score distribution learning method. We further extended it to a multipath model to utilize the fine-grained score labels. Our methods set new state-of-the-art on 3 datasets for action quality assessment. In the future, it's interesting to explore the interpretability of our models and apply them for instructional video analysis.